Hello, everyone, and welcome to today's webinar, Automating Co-Simulation of High-Fidelity 3D and Reduced-Fidelity Surrogate Models for Fast Design Analysis using CoTherm. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Joshua Pryor. Josh is a Senior Engineer and the Product Manager for CoTherm, TAI's CAE coupling and process automation software. His primary focus is developing models and simulation processes using Pytherm, CFD, and other CAE tools, including applications such as climate control and thermal comfort, vehicle thermal management, and surrogate modeling. Josh has been with Thermal Analytics since 2006 after receiving his BS in Mechanical Engineering from Michigan Technological University. Throughout today's presentation, which we will review at the end, we are also recording this webinar and will be sending you the link following this presentation. And with that, Josh, if you're ready, you may begin.
Great, thanks, Chris. Hello, everyone. Thanks for joining today. Yep, you've heard the topics. We're going to be showing some recent updates and advanced features in CoTherm and using those to show some workflows around different fidelity models and surrogate modeling techniques. So let's jump into that. Here's an outline of what we'll cover today. I'll spend a little time on some background and context. What is the problem we're trying to solve here, and why do we see the CoTherm software as a good fit for that? We're going to use a demo application, some models for the purpose of cabin climate control and human comfort that we'll use throughout the different techniques we're going to demonstrate. We'll go through some co-simulation of those models, creation of a reduced order surrogate, and then some optimization using that surrogate, fast running surrogate that we've trained. Throughout that, we're going to be showing some of the latest CoTherm features that have either enabled or streamlined some of these approaches, and then talk about how to get started and use these sort of workflows on your side. Okay, so the context here is that anyone working in this area of CAE more generally, or specifically the sort of thermo and fluid CAE models we're going to be looking at, that often requires a variety of different modeling and process techniques, especially if you're working on these problems in the context of a long product design cycle. So those might involve creating models of your product at different levels of fidelity and including different physics, and trying to trade off or optimize the relationship of the model fidelity and its accuracy, or on the other end, how fast can you turn around results and run more iterations. And often that might require co-simulating models using different physics that have some complementary nature to them, like the thermal and CFD coupling that we'll be showing today. The example application, again, is going to be automotive cabin modeling, where we're interested in climate control, HVAC system details, and also human effects, both thermal physiology and comfort. And then we also want to consider those effects in the context of energy usage and efficiency. So again, at certain times when looking at an application like this, you might need high fidelity models to look at complex local effects. The common example around a cabin would be looking at how does the local 3D variation in the cabin air temperature and the flow field affect things like either the local or whole body thermal comfort, the occupant's perception of that cabin. And to do that, we might need a high fidelity CFD model like this slice through a volume mesh we're showing down here, and a good representation of the HVAC system, both its inputs and details like register aim, things like that. But then on the other side of the spectrum, we might also need some fast running models if we want to do some optimization or explore a large design space with a lot of uncertain variables. So if we want to look at something like how can we minimize the energy usage of the HVAC system while also maximizing thermal comfort, that might require quite a few simulation iterations, which might not lend itself as well to these high fidelity models. So and then the question that we're going to try to answer today is, how can we get the best of both and apply the right tools at the right time? So some of the modeling tools and techniques we're going to be covering, we'll be using our own CoTherm software for the 3D thermal modeling, including the CoTherm human extension that'll give us a good representation of the human's thermal physiology response and also his thermal comfort response. And on the cabin side, that'll also be accounting for the external environment and all the radiation and conduction heat transfer. We'll be using a CFD model for the cabin interior air to represent the flow field distribution and modeling how the flow boundary conditions coming from the HVAC system interact with the cabin. Our demo models are going to be using StarCCM+, but everything we're showing could easily translate to other CFD tools that are supported in CoTherm. And then we're going to bring in some Python-based machine learning and surrogate modeling techniques using some commonly used Python libraries. And then our environment to bring all those together is going to be the CoTherm software, which has integrations and tools to work with all these techniques in a variety of ways. In case you're not familiar with CoTherm, this is our process automation software that's been on the market for a number of years now. CoTherm is a either graphical or batch mode desktop software, and it is designed for very flexible co-simulation and process automation. It uses this visual task-based process canvas to let you lay out the different steps in your process and connect them with various kinds of logic or iteration. And it has a number of different tool integrations, and the end goal is to put together, these different kinds of processes that are listed here. So helping you automate co-simulation, exploration of a design space, optimization, analysis of the results that come out of those things, and also more general automation for setting up models or more complex workflows. This slide just briefly summarizes some of the different tools and capabilities that CoTherm has. In terms of software tools, we of course tightly integrate with our own thermal software, so CoTherm or Musis on the defense side. It works with several 3D CFD tools with native integrations for StarCCM+, Fluent, and OpenFOAM, and other tools as well. It works with system models via either the Open FMI interface standard or natively with the MATLAB Simulink environment. We also work with a number of engineering productivity tools, Excel, and so on, and other custom tools that you can integrate. The Python programming language is a big part of CoTherm's ecosystem. We both use it as a modeling tool, like we're going to be doing today with some of that surrogate work, and it's also used for all the scripting and journaling that's built into CoTherm. Those different capabilities can be built up, again, to support processes for the purpose of model coupling, doing things like design of experiment and sensitivity studies, surrogate modeling that we'll show along with optimization, and also model setup automation. So our example cases, these are the cabin models we're going to be demonstrating today. So thermal and CFD simulations of an SUV. We've got a single human occupant in the driver's seat, and we've set up the HVAC system representation in the CFD model for primarily panel flow, and then also some second row vents. We've got this model set up for a hot weather cool down in Phoenix conditions in August. So pretty hot weather, high solar load. The top image here is actually an animation of the solar fluxes absorbed by the vehicle over the half-hour cool down period we're going to look at. So our scenario is that the human enters that vehicle with the vehicle at an elevated temperature. We turn on the HVAC system at the same time. And then during the cool down, we're looking at key results of time to comfort and local thermal comfort effects on different body segments, and then also the energy usage of the HVAC system. So first, we'll look at using CoTherm to just simply do a transient co-simulation of those two models. The coupling approach that we want to take here is a transient stepwise coupling. So we're going to set up both these models to run in transient mode. We are going to freeze the flow equations on the CFD model, since in this case, we're not changing the flow boundary conditions. So we can just compute a steady flow field, and then the transient changes will just be in the thermal field. But that regardless, we're marching both codes forward in time and then defining these exchange intervals where we map thermal and convective boundary conditions between the two codes and continue marching forward. So we can get good convergence of the co-simulation by controlling exactly how fine or how large that interval is for the coupling data exchange. So let's jump over into the CoTherm software and take a look at one of these processes for transient co-simulation. So I've got a CoTherm process here that has already been set up for co-simulation. This is a pretty off-the-shelf application of CoTherm. Right now I'm in what's called the analyst layout, which is a simpler layout for when a process is already set up and you just want to get things running. On the canvas here, you can see I've got a loop of tasks where each pass through this loop represents one of those coupling intervals. So that'll repeat until I get to the end of my transient scenario. And then most of the work for that process happens here in this run simulations block, which is what CoTherm calls a sub-process group. And that contains different threads for running the thermal model and the CFD model, and then doing some bookkeeping. And the threads within that we can choose to run concurrently or one at a time. This pane here on the left, the key properties, shows all of the inputs I need to worry about to set up the co-simulation. So CoTherm needs to know where the software is installed for both TiTherm and StarCCM+. CoTherm is going to manage the parallel configuration. So there are properties here for the number of distributed processes to use for each code, and if they're to be run on remote hosts, what those host names should be. For the models to be coupled, they're just file paths to browse to for those models that have already been filled in. And then an important part of coupling are these selection resources. These are filter rules to control which parts participate in our co-simulation. So if I open these up, there's a dialog here where I can add one or multiple filters to choose which parts are going to be coupled. Those filters can work on either a part or a group assembly basis. And then I can create rules to specify parts which are coupled on their front face in TiTherm or their back face or both. And then the rule to match those parts can be an exact match or a prefix or a suffix or an open filter. So in this case, for my TiTherm selection, I've got one rule that is going to link this CFD front assembly. I've already scanned this model, so I can see in the preview here that that assembly is matched in the thermal model, and it's picking up 88 parts to be coupled. Then I've got a similar selection for my CFD model coupled parts, slightly more complex selection here with 8 filters. In this case, I've started off with a filter that has a star, so that indicates set up all of the boundaries to be coupled and receive temperatures from TiTherm's front face. And then I've added a few exclude filters for some boundaries that should not participate. So then down here, and again, I've scanned this model, so I can see a preview that in my fluid region, I've got 82 parts that are set up to be coupled. Again, receiving front face temperatures from the TiTherm model. Then this process needs to know a start and an end time for the transient coupling. And then within that, there's a table here to control the coupling interval and the time step sizes for each solver. And this is a table so that I can change the coupling interval over time. This table is interpreted as a step change. So it's going to start on the first row here. It's going to couple at a 2-second interval between the codes, using a 2-second time step size for the thermal solver and a 1/4 second time step size for the CFD solver. And that'll continue until we reach this 10-second mark in the second row. Then we're going to bump up the coupling interval and the time step size for each code. And that'll continue. And as this, so we're using a small coupling interval at first when the changes are sharper. And then as this approaches more of a steady problem, we can use a much larger coupling interval and increase the efficiency of the simulations. Beyond that, mostly just minor coupling details, timestamps for the thermal model since it's using the natural environment. There are a number of controls over extra files to write out and which order to run tools in. Then also controls around exactly what kind of data to extract from the CFD model for the convective conditions and pass over to TiTherm. I've run this model previously, so I'll go back to the presentation here and we can take a look at some results. So after that simulation completes, on the left here, we have an animation of the surface temperatures from the TiTherm model looking inside the cabin with a clipping plane. So you can see the temperatures cooling down from that initial hot condition. And, especially here, like on the human, on the neck and face, we're getting a lot of cooling with the HVAC flow aimed at that area. The images on the right show the heat transfer coefficients that are being mapped in from CFD. Again, you can see the high heat transfer is around the upper chest, neck area based on where that's aimed, and a bit here on the left hand, which is also directly in that flow. And then this bottom image here shows the solar flux on the human. So based on the position and some of these parts that are closer to the window, we're getting some high solar load on the left upper arm, shoulder, and the left thigh, and modest loads on a few other areas. Then let's look at some comfort results. As a quick reminder, for the most part, we're going to be looking at Berkeley comfort outputs from these models. The Berkeley comfort is one of the outputs from the CoTherm human model. It's a very powerful one because it separates the concept of sensation, which is how cold or hot a body part feels, from the concept of comfort, which is how positive or negative, how good or bad that sensation results in being perceived. So both of those metrics use a -4 to +4 scale, but they have a different meaning. Again, sensation being warm and cold, and comfort being comfortable and uncomfortable, or good and bad. So here's some Berkeley comfort results from that first coupled simulation. The overall sensation in blue, so very warm when we enter the car, cools off very quickly with the HVAC turning on. We cross over neutral thermal sensation at basically a minute in, and then we are slightly overcooling. We're steadying out at a value around -1.5 or somewhere in that range. And as a result, the thermal comfort, very low at first, jumps up with corresponding to the sensation. And we don't quite get to the positive side of thermal comfort where we'd want to be. So we've at least reduced the discomfort, but not extremely comfortable yet. We could then dig into all the local results to try to explain why that is. This chart here shows the same overall comfort in the light blue line here. That corresponds to this orange line we were just looking at over here, but just for the first 5 minutes of our cool down. And then the partial lines around that represent the segments that are contributing to the overall comfort. So the overall comfort is a complaint-based metric. So it's mostly going to be driven by the 2 or 3 least comfortable segments. And it looks like after a few minutes, the least comfortable segments are the head, which is down here in orange, the right hand in dark blue, and then the face over here in gray. So that's kind of what we need to address if we want to improve that overall comfort. If we look at then the local sensation of some of those problematic segments, sure enough, on the face and head side of things, the problem is actually getting too cold after the first few minutes. The head is dropping from warm to cold very fast and remaining pegged at kind of the most cold. The face is getting down into the -2, so moderately cold. And the neck is remaining a bit closer to neutral, but even there, we're colder than neutral after about 5 or 6 minutes. So if we want to update our simulations to not just have a static HVAC condition that's going to kind of overcool after a few minutes, but a more dynamic condition that we could either prescribe or hook up a controller to, how might we do that? So the first thing we'll look at is kind of extending our thermal CFD coupling to account for some transient HVAC conditions. To understand that, I'm going to come back to a couple of other concepts that are built into the CoTherm software. First, variable update and assignment. And these are concepts that we use to explain how we get data from a model into CoTherm or push data from CoTherm into a model. So variable update is the former. That's where we have some value that has been stored or computed in an external model, and we want to import or bring that into CoTherm. And variable assignment is the reverse, where we've got some value that CoTherm is aware of, and we want to push that out into a model to use it as an input or a boundary condition or parameter. There are generic tasks that are used for both of those. The variable update task works by just a list of updatable variables, and you can check which one you want to update. When CoTherm reaches that point in the canvas, it'll import those values and then also append them to the monitor history so you can keep track of how they change over time. The variable assignment task works by adding, one or multiple assignable variables, and then also choosing on the right-hand side of this list which data to assign it to, or the source of data to assign into that. So this is similar to kind of like just in a programming language where you'd say variable equals value. The left-hand side is the variable that we're assigning, and the right-hand side is the data value that we're going to push. So in this example, we're assigning some data into these two MATLAB variables from two Excel variables that presumably we've read into CoTherm earlier. So same thing, when this task is reached on the canvas, it'll perform this variable assignment, and in this case, push that data out into MATLAB. But we're going to use that to set up our thermal and CFD models. To support that, in the spring release that's just coming out this week, CoTherm has some new input variables for model setup automation that relate specifically to Fluent, StarCCM Plus, or TiTherm models. So in the add menu, you'll see these 3 new input variable entries in this release. Each of those variables allows you to associate it with a model and then scan for the type of value that can be assigned. And they, again, correspond to curves for TiTherm models, or field functions in a StarCCM Plus model, or an input parameter in a Fluent model. With all 3 of those, you can, once you link it to a model, you can scan that model to see which of those abstractions is available and choose the one that you want to assign from the GUI. And then once that's set up, you can use this in one of those variable assignment tasks. So in this case, variable assignment is going to push data out into one of those field functions or curves to update its definition. And then that's useful for if you want to loop over a table of values, or like we're going to in this example, change a value over time, and you want CoTherm to manage that boundary condition. Makes it very easy to do. Has applications across any type of process where you're creating a sweep of models, like a sensitivity study, or a surrogate model, or drive cycle analysis, where we're setting up steady conditions. So let's look at an example for that with our transient coupling process. What we want to do is kind of start from the process we just had, which was set up to do co-simulation and then march forward in time, and then add some additional logic to that. So we're going to couple just as we were before for the first minute and 35 seconds, because that's about how long it took for the human to start to be overcooled on some of these segments. Once we reach that time, we're going to have CoTherm unfreeze the flow equations, and then make a change to both the vent aim, so kind of the angle the flow is coming in based on the registers. And we're going to try to aim that more at the torso level instead of the face. And we're also going to reduce the flow rate by 15%, and then continue our coupling. And then for efficiency's sake, we're going to let that run with unfrozen flow equations, full transient up until 6 minutes have passed. Then we're going to say that's good enough for the flow field to converge. We're going to freeze the flow field again, and then continue our coupling. So this is sort of the virtual representation of the logic we want to do. Let's take a look at how we can do that in CoTherm. So here I've got a similar variation of that same transient coupling process we were looking at. Again, we've got this loop where each pass is coupling with one interval, and this task here is doing the work of running the thermal and CFD models. In my document tree here, I've added 2 new input variables that correspond to those 2 values I want to change, the flow rate and the vent aim. So I've pre-configured my CFD model to use some field functions for the boundary conditions for those 2 values, so then I can just update those field functions from the CoTherm side. So if I open up this dialog, I've already scanned my star model, and I can see the different field functions that are available. I can just pick them from the list to set them up for this variable. And same thing here for this vent aim z height that's going to be used for a velocity vector on the inlet boundary conditions. Then we also need values to set for these inputs. So for this first simple case, again, I'm just kind of making a step change in those boundary conditions. So I've got 2 expression variables here called modified HVAC flow rate and modified vent aim z height. And these are the placeholders for the updated values I want to set. So those numbers are just associated with those resources. So then to make use of that, if I browse in here to the run CFD task, these extra tasks here sort of represent that additional logic. So there's a decision task here that checks when I've reached that, that time at which I want to change the HVAC conditions. When that condition evaluates to true, it's going to run this task, which is a variable assignment. It's going to update those two field functions with my modified values. It's going to use a macro task that's been added here to unfreeze the flow equations, and then that'll eventually come back here to the normal process logic and continue. And then there's an additional decision task that says, after all that has completed, if I've reached that 6-minute time when I want to freeze the flow again, then it's just going to run another macro to freeze those flow equations to speed up my transients. And then again, it'll move on with the coupling. And again, this entire set of tasks is being repeated on each coupling interval based on this loop that I've got up here at the top level. So we've run that case as well. So let's jump back here to the presentation and show some results from that case. So I've got a similar surface temperature animation that we looked at from the first pass. And then this animation here is showing the now transient heat transfer coefficients we're getting from the CFD model. So you can see again, just for the first few seconds, it's got that high aim with high convection around the upper shoulders and face. And we change those HVAC conditions. The results fluctuate a little bit. This animation is coming from the CoTherm side, which has a larger time step. So we're not seeing all the transient changes on the CFD side in the animation. And then that steadies out. So now we've got the highest convection just around the torso here. So that kind of did what we thought it would in terms of convection. Let's see how that looks on the thermal comfort side of things. These plots show a comparison of the thermal sensation and comfort. This upper plot has the thermal sensation of our first pass in blue, and then our updated run with dynamic conditions in orange. So sure enough, when that flow is changed, that creates kind of a transient spike up in the thermal sensation. So it makes you feel warmer, and then eventually kind of comes back to the same trend. And interestingly, does get slightly below the original baseline after about 8 or 9 minutes here, although not by much. And then thermal comfort, that also oscillates a decent amount after we change those conditions. We see some spikes above the original value. The new value here is in yellow, and some below. But then after about 7 minutes here, we do see a consistent increase in the comfort, and it's actually on the positive side of the scale now. So we did improve the comfort, but by a pretty modest amount. And again, we could look at some local values to see why that was. With the face segment, which was getting a bit overcooled before, we did improve that, kept it closer to neutral for longer. We are still getting down close to -2 with that segment. With the neck, this one was actually not too overcooled before, and now we've kind of kept that on the warm side throughout. So kind of leveling out, still on the positive side, the warm side of some sensation. And then if we look at some other segments away from the face and head, so for example, like the right hand here, this is looking at local sensation just from 0 to 4, so on the warm side. And our first pass, the right hand was staying pretty warm already, only getting down to about a +2. And with our change, it's actually staying up at a +3. So although maybe we've made some things better around the face and the neck where things were problematic, maybe our change has made the local comfort a bit worse in another area, which is again, one of the benefits of the Berkeley comfort output is being able to understand that. So doing that coupling with dynamic changes to HVAC conditions did modestly improve the comfort and the energy use. But if we want to make that more realistic or more controlled, we're going to need to make more than one change, that step change, and we might need to be better informed rather than just kind of making some guesses about how to do that. So this workflow did let us look at some of those thermal comfort effects, but the efficiency and the scalability of that are going to be limited. This bar chart here shows a comparison of how much CFD runtime was used for those two conditions. About 25 minutes on that first case using 32 CPUs, and this one was with the flow equations frozen throughout. And then just unfreezing those for a few minutes basically doubled our CFD time. So if we were going to change the conditions more dynamically and run the full transient for longer, this is just going to get less and less efficient. We can probably manage it for, an iteration or two, but if we want to try a lot of variations, that's not going to scale well. So how can we turn around those results more quickly and add more automation or optimization to this approach? And the technique we're going to look at next is then fitting a surrogate model to our CFD to speed up the simulations. So we'll show a few CoTherm features and processes that are designed for just that purpose, to train a surrogate model. So if we're going to train a surrogate model, we need to sample the high fidelity models. And to do that, we're going to use the CoTherm DOE table feature. A DOE table allows you to specify some ranges for variables and then have CoTherm generate some sample points. Those points can be generated based on a couple of built-in methods or any custom method you define. That table is going to consist of these DOE columns, where each column is an input or a factor, to our DOE, and it just needs a minimum and a maximum value to be specified to know what range over which we can create sample points. And then once we generate some sample points, we can see them in either a table or a plot view that we'll show. So that DOE table is a building block then for a surrogate modeling process. And here we're kind of taking, again, a data fit surrogate modeling approach, which goes by some different names, including a response surface model. But the idea here is to start from a high fidelity physics model that's slow to run and might have many, dozens or hundreds or thousands of inputs and outputs. To do some down selection based on the most influential inputs and a few of the outputs that we care about. Then exercising that high fidelity model over a reasonable range of those inputs to create some training data so that our surrogate model can understand how the high fidelity model behaves. Then once we have that training data, we'll fit a surrogate model based on those results. And the end result is going to be a fast running surrogate based on potentially a variety of numerical techniques, which can predict our down selected outputs based on new combinations of our down selected inputs. So this is useful for doing things like optimization, sensitivity analysis, uncertainty quantification, or creating a representation of a 3D model to couple with a faster 0D or 1D system model. So for going through that surrogate modeling process in CoTherm, again, we're going to use a DOE table to define our inputs and generate some training points, and then we'll be able to visualize those. After we have those sampling points, we'll execute the simulations and we'll be able to plot some of the results from those sampling points directly within CoTherm. Then once we've got that training data, the CoTherm process keeps the inputs to the surrogate pretty simple. There's basically just a list of different surrogate model types that you can choose to fit. So if you know a specific numerical type that's going to work for your problem, you can just choose that, or you can choose them all and let CoTherm find the one which works best for your problem. And then once we've got a surrogate model, we're going to use some additional visualizations and plots to evaluate how accurate the surrogate model is. And we'll get more into this when we go into a live example here. So that surrogate workflow for our specific problem, again, our goal here is to eliminate the bottleneck of the CFD simulation. And really what we want to get out of that is the convective effects on the human. So our down selection process in this case, we're going to choose 3 key inputs to the CFD model: the airflow rate for the HVAC system, that vent aim Z vector, so basically how high or low the panel registers are aimed at the human, and then the vent temperature at the panel inlet. And then based on those 3 inputs, we want to get outputs for the heat transfer coefficients. We're going to choose to average the local heat transfer coefficients to segment level values. So we're going to get an average value for left lower arm and right foot and all the different body segments. Since that's the resolution our thermal comfort model is at, that coarsening will let us simplify the outputs a bit. So we're going to set up a CoTherm process to exercise those 3 variables over some reasonable ranges. We're going to end up using a little under 300 sample points to exercise the steady model. And then we're going to end up training, in this example, a neural net-based surrogate to predict those convective outputs based on new inputs. So I'll jump over to CoTherm and show a little bit of what this process looks like. So in this case, the process canvas, we've got a loop of tasks up here, and this represents where we're going to exercise the high fidelity model with the DOE table. So each pass through this loop is going to generate results for one sample point. Then after that completes, we've got some sub-processes to train the surrogate model and then do some statistical analysis on the results. In terms of the inputs, here we're just running star. So again, we need to know where that software is installed and what parallel configuration to use for it. We've got a steady state version of that CFD model we were coupling that's set up with those field functions that we can exercise. A key input here is this input table. This is the DOE table. So if I open up a dialog for that table here on the column editor, I've got my 3 factors. So HVAC flow rate with a specified range, HVAC vent temp with a specified range, and then that vent aim Z height. And then I'm using the optimal Latin hypercube method to generate the points. I've already generated them here, so I've both got a table view of the data and a DOE plot. The optimal Latin hypercube generates points that have a bit of a random nature to them, but are designed to be spaced evenly from each other in the multi-dimensional space of the 3 variables. And the positioning of these points, you can kind of think of this as like rooks on a chessboard that couldn't attack each other. So we're evenly sampling each of these ranges and then placing points under those constraints, and again, trying to get them evenly spaced. This DOE plot shows me scatter plots of each combination of variables. So the diagonal here, you end up getting a variable against itself. So that's always going to be a diagonal line. And then on the off diagonal, I can see how the sample points for flow rate and vent temp relate to each other. But again, that table can be generated in a couple of ways and manipulated manually as much as you want. But the point is just to get data in here that'll give us training data for the surrogate. On each pass through the DOE, we need to set those sample points as inputs. So we've got another one of these variable assignment tasks that's linking those 3 field functions on the CFD model to the 3 column variables that we just looked at in the table. So that'll update the CFD model each time. And then we've got another task here that tracks the outputs. So another thing we've done is, again, we want to get those heat transfer coefficients out of the CFD model. So we've created reports in the CFD model that CoTherm can use as output variables. We've linked all those reports, and then they're updated here. So that's where those outputs are being tracked for the surrogate model training. Further down here in the key properties, this is that table where we can choose which surrogate model types we want to include. So in this case, we've got 10 total surrogate model types we're going to try, and then CoTherm is going to choose the best one that most accurately predicts the resulting data. So this process does have results in it, but I'm going to jump back to the presentation here to show a summary of that. First off here, this is just sort of a graphical representation of what we're getting out of the surrogate model. So the CFD model is going to predict these local variations in heat transfer coefficient, like we're seeing in the left of each of these set of 3 images. And again, to simplify it, we're averaging those values to the segment level. So the middle image out of each group of 3 is the original CFD prediction, but just averaged to the segment level. And we're also using a slightly different color scale there coming out of CoTherm. So that's another reason that looks a little bit different. And then the third image out of each is the surrogate model that we trained and its prediction of the segment level values. And that also relates to these validation charts on the bottom here, where we're looking at for each body segment, the surrogate prediction with the orange scatter points, and then the original results are the blue diagonal line. So if the surrogate was working perfectly, the results would collapse onto that blue line. So we can see a little bit of that variation in the plots. Here in the color scale, looking graphically, the surrogate model looks pretty visually identical. So again, we're trying to pick up this high convection in the upper body when the conditions are aimed that way. This middle case has a much lower aim vector, so we get the high convection around the lower torso abdomen area. And then this final case just has a much lower flow rate and still aimed at the face. So the highest convection is still upper body here, but much lower values than in the that high flow rate case. Here's some results from that surrogate process looking at the different surrogate model types that were attempted. And for each of these model types, the chart on the left here shows the model score, basically an R-squared value between the cross-validation results and the original results. So higher is better. Our most accurate model turned out to be the neural network. Least accurate was the elastic net, and you can see a range of scores in between those. But then another interesting thing is that these more complex models take much more time to train. So the chart on the right is showing the training time in seconds. So the neural network was the most accurate, but also the slowest to train. And this is on a log scale here, taking almost 2 hours to train. Whereas there were models such as gradient boosting that were nearly as accurate and only took about a minute to train. So if training time was a concern, you could choose a different point in this to get slightly more optimal results. Next here, we've got some plots that show some further cross-validation and information from the surrogates. So we can show a couple of interesting things. These plots are generated automatically in that CoTherm process. On the upper left here, this is a learning curve plot. So this shows both a training score, which is sort of accuracy on known data, and a cross-validation score, which is accuracy on unknown data, as a function of sample points. So this is created by training the surrogate model with a reduced number of sample points. So the point on the far right is using our full DOE table. And then if we take out some sample points, how much worse does the model get? So this helps us understand, if we have enough training data, or based on the slope of this curve towards the end here, if more training data would get us a more accurate surrogate. Then these other plots are cross-validation plots for specific outputs. So for example, this plot is showing for the face segment heat transfer coefficient. The diagonal orange line is the expected results from high fidelity, and then the blue scatter points are the surrogate predictions for the equivalent points. Turns out the face segment was one of the toughest ones to train out of our group. If you compare that to like this plot for the chest heat transfer coefficient, that one collapses down a bit more, or maybe something like the left hand that's a little bit in between. These three plots are all from cross-validation cases. So what we're doing here is splitting out the DOE data, taking 80% of it to train the model and withholding the remaining 20% to test the model on unknown data. And then all these scatter points are taken from when that point was within the 20% test data set. So showing how the surrogate model predicts when it doesn't know the inputs. Another neat thing we can do with this process is look at the sensitivity metrics of the different outputs. I won't spend too much time here, but this chart shows the sensitivity indices to either the HVAC flow rate in blue or to that vent aim vector in gray for each of our different outputs. So this is neat to see where some of these segments are about equally sensitive to the flow rate or the aim, or you see some segments like the arms here that are much more sensitive to the flow rate, presumably meaning they're either sort of out of the main plume or always in it, and therefore not as sensitive to the aim vector. And then we see some where actually the aim vector is more important, like some of these abdomen segments here that are presumably getting significant convection even with lower or higher flow rates. I'm not showing the sensitivity here to the vent temperature, since that turned out to be a much lower influence than these two variables for most outputs. All right, so now that we've trained a surrogate, let's do something interesting with it. And at this point, we could hook up this surrogate to a controller model or a 1D coupling process. But in this case, we're just going to use CoTherm's optimizer to try to find optimal HVAC conditions for thermal comfort and energy. So CoTherm also has a an optimizer built in. This is based on the Dakota technology, and it allows you to optimize a group of tasks using multiple local and global methods and find the optimal combinations of some inputs based on a function that you provide. How we're going to set that up in CoTherm is we're going to use the surrogate model that we just trained in conjunction with CoTherm. So the surrogate model will give CoTherm its convective inputs. And then we're going to put that into an optimization loop where we let the optimizer choose the cooling power, the flow rate, and that aim vector for the HVAC system and try to find the best comfort. To close that loop, we need a cost function for the optimizer to work on. So we're going to define an optimizer cost function that is a weighted combination of the opposite or the reverse of thermal comfort, so that a higher comfort will give us a lower cost. And then we're going to combine that with a term based on the HVAC power. So lower power will give us lower cost. We could tune that function a bit for how much it's optimized to try to get better comfort versus lower energy, but we're trying to kind of balance it for this example. And then that we're actually going to repeat that optimization for each transient coupling interval. So just like in the transient coupling case, we're going to advance the codes, but now we're going to repeat that advancement many times through the optimizer to try to find the best conditions. So one last CoTherm process to show that will demonstrate that. I've got another process that again will look like our transient coupling processes, where again we've got a loop over each of the time intervals. But now I've got a task here, which is an optimization subprocess. And what's inside this is going to be repeated by the optimizer until it finds the best. That optimizer needs to know which variables to optimize. Those have been already set up for those three we just mentioned. So those are checked here and their ranges are defined. And then it also needs to know a cost function. So we've set up an expression that'll calculate that for us. So this comfort cost function is just a mathematical expression that references symbols for the Berkeley overall comfort output that we've linked up to this process and the power that we're applying to the HVAC evaporator. So those are the two terms we just mentioned. In terms of further structure, so then if I go inside this optimizer task, I'm going to see that all it's doing is that same run simulations task from before. But now that run simulations, rather than having the slow CFD model, that's been replaced with my fast surrogate model. So for each pass, it's going to run the surrogate to get the convective conditions and then pass that into thermal. And then inside those, we've got, again, the same sort of variable assignment tasks to set the inputs for the surrogate. And then when we get over to the thermal model, it's using the same sort of input variables that now represent CoTherm curves. Those curves are going to be set up based on the outputs from the surrogate model. So that'll be automated with the latest conditions each time. So let me jump back to the presentation here and I'll show some results from that quickly. This chart here on the left shows what the optimizer ended up choosing over time for those three parameters. So the cooling power, which is shown here in blue, the optimizer kind of picked up on the overcooling and dropped that cooling power down quite a bit. That's plotted here on the right axis. For the air flow rate, which is shown in orange, it also backed off on that. So it seemed to be picking up on the unnecessary convection on some of these parts and backing that off. And then the vent to aim, it kept that pretty high throughout. That's the gray line here. We started off at a face aim. It did drop it down not too far, maybe to the shoulder level, and then also gradually brought it back up. But again, this is at a lower flow rate, so not as much excess convection as we had in that first case. So then how well did the optimizer do in terms of comfort? This chart here shows the thermal sensation. The orange case is our optimized case. So interestingly, the optimizer ended up keeping the sensation slightly warm throughout, kind of leveling out at a +1 value here, which makes sense given that we told the optimizer to also try to reduce the energy usage. And then if we look at the comfort, the optimized case being in yellow, we actually kept a pretty similar trend to our original case, although we, except for some oscillations, we do have a slight offset of, maybe half a point or a quarter of a point at different phases here. So a slight increase in comfort. So the optimizer was able to modestly improve comfort, but use a lot less energy than our baseline conditions. And again, we could tweak that cost function to make that behave a bit differently. So wrapping up, if you're interested in trying out CoTherm for a bunch of these examples, we maintain an extensive set of example processes that are included with each version of CoTherm. So if you browse in the installation directory, you'll see all these example processes. There's also an experimental category of processes that are still, a work in progress in some ways. The default installation will have just the process documents, and then you can also download a zip file from our support site that has all of the model files if you want to try that out. Everything we showed here today is demonstrated in different pieces of examples. So these are all workflows that you can pull off the shelf and try out. These examples are going to be the best case or best place to start off, even if you're going to add a lot of customization to a process. So you can hit either of these links here to read more about that or download the software and examples from our support site. So conclusions from today. So again, we're coming from this perspective where to be effective with CAE, we may need a variety of simulation tools and techniques in terms of their level of fidelity and simplifying assumptions. And tools like reduced order modeling, surrogate modeling can be a really powerful technique for getting key results based on high fidelity results, but accelerating how quickly you can generate them on new conditions. And CoTherm is a platform. We're always trying to extend it and make it more capable for these variety of techniques and to try to give you all the tools that are necessary to execute these different kinds of co-simulation or automation. So thanks for your attention, and I can take any questions you've got now.
Okay, thanks, Josh. Let's see, first one here. Why does a surrogate model more accurately predict some of the outputs and not others?
Yeah, good question. We were showing the better cross-validation on some segments than others. We didn't analyze that too closely, but I think one large factor is, again, with the way that we were averaging the results to segments, some of those segments had much higher variation and much different conditions. Something like the face that was, partially getting impingement and partially shielded from the HVAC plumes. Other segments were much simpler. So there's probably some room for improvement there in terms of exactly how we chose to average those parts, rather than just using the simple body segments. We could, group those areas based on similar results and probably improve that a bit.
Okay. How was the vent aim controlled? Was it using HTC values? And if yes, were the HTC values from star CCM or CoTherm?
So the vent aim was, so when we trained the surrogate model, the vent aim was just an input to the CFD model, right? So you, of course, in a more complex model could actually have registered geometry. This was a simple model where we were just imposing a vector for the inlet flow. And so just using a field function to change sort of the Z component of that vector. And then once we got to the optimization case, we were controlling that, we showed that cost function that was based on the comfort and the energy usage. So we were controlling it based on the human results indirectly. So the optimization, tries out a value of that vector, sends it to the surrogate model, which updates the heat transfer coefficient, and then the comfort results are what then end up closing the loop with the optimizer and giving it the feedback to choose the best value of that. So it's a bit of a hypothetical situation, not trying to represent a real controller in a vehicle, but sort of a hypothetical optimizer that could find the best value. But again, the point there was just to show that we could dynamically change that value, and then you could apply the same thing to a controller model or some other situation.
All right, thank you. How do I manage communication between a custom software, e.g. my own, and CoTherm? Which interface do I need to support with my software?
Yep, good question. So there are several different levels at which that can be done. you can, the simplest is generally like a command line interface. So any tool that has a command line or batch syntax, you can hook that up as what CoTherm calls a console tool and use dynamic symbols to manage the command line parameters that are sent. Another pretty simple version is if the tool has any kind of like Python-based API. Since CoTherm has native Python journaling and scripting, you can either just use generic Python code or import new libraries into CoTherm's Python interpreter that are specific to your code and hook that up. And then the more advanced solutions may involve more investment, but yeah, at some level you can, there are different levels of API and SDK that can be applied to integrate any tool. But command line and Python based are the most common ways to handle those custom tools.
All right, thank you. What was the runtime of the optimized transient run using the surrogate model?
Yes, so didn't mention too much about the hardware details of that, but for that optimization case that was just running the surrogate, we no longer need, a cluster since we're not running the CFD model anymore. So we set that up to run on a workstation with 8 cores. And with the way that the optimizer was set up, we're basically doing about 30 different optimization cycles. And then each cycle, we're allowing the optimizer to try about 75 different iterations to find the best, just to give some context on how much we're doing there. And under those settings, on a workstation, it ran basically in an overnight run. So in the neighborhood of 12 or 16 hours or around there. The bottleneck at that point, since the surrogate is very fast, becomes the CoTherm model. So you can also accelerate that by how coarse or finely you mesh the CoTherm model.
Okay, thank you. Does CoTherm support COM interface?
We don't have any built-in resources or tasks for COM right now. So if you were interested in that sort of interface, you'd probably need to link up to that with one of those other integrations mentioned previously. But yeah, for that specific question or any others about linking to CoTherm, feel free to reach out afterwards and we can have some further detailed dialogue about how that could be done.
Thank you. Can this study be done with rapid flow? Would that be faster to train than with CFD?
Yeah, so we've got the new rapid flow extension that's also coming out with this release that we'll be talking about a bit in next month's webinar, actually. But yes, since that's another 3D fluid dynamics application, you could follow exactly the same process and just swap out what the fluid dynamics model is. Since that approach is also designed to be a little bit faster, you could probably also open that up into other techniques, just trying to use that model with a very coarse grid or redefine the surrogate inputs and outputs a bit. But there would definitely be multiple possibilities.
Okay, well, thanks, Josh. Looks like that's it for questions. So that will complete today's webinar. We appreciate you all for attending. Everyone will receive a follow-up email this afternoon containing links to download this presentation, slides, and watch the recorded webinar session. Again, thank you, everyone. Thanks, Josh, and have a nice day.
Thanks, everyone. Talk to you later.